In this video, we're diving into Blender's bump node. You might have noticed in a recent dot update to Blender 4.4, a new parameter appeared on this node called filter width. It's caused a bit of head scratching for some folks, myself included, when it first appeared. In fact, I did a video showing how to avoid issues with it, but at the time I didn't fully understand what it was doing, but I do now. So, we're going to break down exactly what this new setting does and how it works alongside the familiar distance bump parameter. It actually gives us more nuanced control over bump mapping, but if you don't use it correctly, it can cause havoc on a surface. So, if you're impatient and not interested in the technical bits we're going to look at, here are the key takeaway points from this video. Number 1. Bump mapping in Blender creates a normal map internally at render time from the grayscale source data you provide the bump node. Number 2. It uses the render resolution to determine how finely to do this. Number 3. The bump node's distance value, with its default of 1.0, is way too large, and a value of 0.0001 is actually a much more practical starting default value. Number 4. The new filter width function captures more subtle bump information, a kind of subsampling that can improve bump mapping on a surface. Number 5. When you import old scenes, the filter width is set to 1.0 for backward compatibility. Point 6. Creating a new bump node sets the filter width to 0.1, and distance values are much more sensitive to being set incorrectly if a bump map has a lot of subtle detail or noise. Before we get going into the technical description, I just want to show you what effect filter width has on a surface. Here I've got this sort of leather surface. I've got a bit of roughness on the surface. I think it's 0.23 or something like that for the roughness. And then I've got a bump map that's using a bump bitmap that's got a lot of little subtle bits and detail to it. Now, this is with filter width of 1.0. This is what 4.3 would have rendered. Now, let's change filter width to 0.5 and we get this. Look at how it's capturing more subtle shading information on that surface because the bump is interacting with lighting more realistically. Let's go down to 0.25 and we get that. And now if we go down to 0.1, we get this. So there wasn't as big of a difference between 0.25 and 0.1. But what this is doing is it's capturing much more subtle shading information because it's able to subsample the bitmap data for bump that is then used to create a normal map. So we're going to go into this in technical detail, but I just wanted to give you a sense for what this actually appears like on a surface. So let's jump in now and take a look at just one more example of this chair leather. Here we have another example where our starting point is a filter width of 1.0. which is the backward compatibility value. Now, if we go to a value of 0.75, we get this. You can see it picks up a little bit of what I call secondary roughness. And now let's go to 0.5. And again, it gives us even just a little bit more of that. And then if we go down to 0.25, we're starting to get into the range where I think there's too much of that roughness. But if we take it down to 0.1, which is the new default value in 4.43, we get this. And to me, that's way, way, way too rough. So what I've done, what I think works better, is if I back it off, the filter width, to 0.3, and I actually think that that kind of gives me something that I like. So here inside of Blender, let's take a look at the bump node for this scene, the chair leather. My strength is 1, my distance is 0.00018, it truncates it, but you can see it's 0.18 right here. If you remember earlier, I said that the default starting point should be that 0.0001, and then you make small, fine incremental changes around that to make the bump a little bit stronger or to make it a little bit weaker. But let's just see what happens if I remove one of these zeros and change the strength by 1 order of magnitude and watch what happens to the surface. With a low filter width, it really blows out quickly. And this is one of the things that's confusing, is because Blender's default is 1.0, it's really difficult to kind of know what to do, like where the value is, where the correct value is to use. I really have grievances with their setting the distance to 1.0 when it really should be a much, much, much smaller value like that. So then my filter width is the one that I determined that I liked, which is 0.3. But remember, if you come in and you create a new bump node, let's put that right here, the filter width that they're defaulting to is 0.1. And that's, to me, in this particular case, it's too fine, and you can see it makes the surface a little bit too rough. So that is why I chose 0.3. So let's jump in now and let's take a look at some of the technicalities of what's actually happening. Now, onto the detailed examination of the bump node and filter width. Let's quickly recap how the bump node works fundamentally. Its job is to take a grayscale image or procedural texture and use it as height data. It then cleverly uses this data to simulate bumps and dips on the surface. The key here is that it doesn't actually displace the mesh. Instead, it generates a fake normal map based on that height information. And that's why you plug its output into the normal input socket on your shader. But here's a really important distinction. The bump node isn't just performing a simple one-time conversion of your grayscale image into a static normal map, like you might do in Photoshop or other image editor. Instead, it's actually calculating that normal data dynamically as the surface is being rendered. For this dynamic bump to normal map calculation to work, it needs a value to define just how pronounced or deep those simulated bumps and dips should appear. This overall magnitude is controlled by the distance parameter. We'll take a closer look at distance and strength in just a moment. This calculation depends heavily on your view and the render resolution, essentially how large the surface appears in pixels on your screen. When the renderer begins, let's say you've specified 640 pixels by 480 pixels as your render size, each pixel is like a grid sitting over the 3D data, and that grid helps the renderer to know how to convert bump data into normal data. Keep this in the back of your mind. Before this update, Blender always calculated the internal normal data for the bump effect based directly on the render resolution. You could think of it this way. The amount of detail the bump could simulate was essentially limited by the size of a single pixel in your final render. Now, this is where the filter width parameter comes in, because until recently, we haven't been able to adjust this sampling behavior. The filter width setting essentially allows the bump node to sample the grayscale texture at a resolution finer than the final render pixels. By looking at details smaller than a single pixel, it can capture much more subtle and nuanced height information for its dynamic normal map calculation. The direct benefit is significantly improved bump shading quality, particularly on textures with intricate details. By capturing those tiny, subtle variations in your grayscale input, the bump node can simulate much more accurate surface slopes. This results in noticeably finer, more realistic, and better defined shading across your surface, especially when working with complex textures that have a lot of small details and features. Let's quickly walk through how this calculation happens. When a ray from the camera hits the surface, the renderer first identifies that intersection point and determines the original surface normal at that location. Then, using the object's UV map, it finds the corresponding spot on your grayscale bump texture and gets the grayscale value at that precise location. Now, while that gives us the height at that exact point, simply knowing the value at that spot isn't enough to simulate a bump. To figure out how to correctly angle the normal vector, the renderer needs to understand the slope of the simulated surface at that point. It does this by essentially looking around at the grayscale height values in the immediate surrounding area. Based on how those neighboring values compare, it determines the gradient or slope, and that tells it exactly how much to adjust the original normal's angle to fake the bump. For example, if the texture shows a gentle incline, According to the height data, the normal will be tilted to match the simulated slope relative to the original flat surface. And this is precisely where the filter width parameter becomes our control. If you've brought in a material with a bump node from an older file into the newer version, like Blender 4.43, you've likely seen that the filter width is automatically set to 1.0. This is done specifically to preserve the appearance the material had in previous Blender versions. A value of 1.0 on the filter width essentially replicates the old behavior, where the area the bump node examined to determine the slope was directly tied to the size of a single render pixel. That's how it was hard-coded before we had this control. But here's the critical issue with that filter width of 1.0, especially if your grayscale texture is dense and packed with a lot of subtle detail. That default value is actually too large relative to those tiny features. It essentially blurs over or averages out those subtle details when calculating the normal slope. The consequence? Well, you end up missing or losing some of that fine information, resulting in a loss of shading fidelity. But now, with the filter width parameter, you gain control. You can set this value to something less than 1.0. These smaller or fractional values are crucial because they allow the bump node to capture those fine details that were previously missed. For instance, a brand new bump node added in Blender 4.43 now defaults to a filter width of 0.1. This significantly smaller value means the bump node examines a much tighter area around the point when calculating the slope from your texture. This reduced sampling area is exactly what allows it to pick up and react to those tiny, subtle variations that a filter width of 1.0 would simply average out. You might find that the distance parameter used to be more forgiving when filter width was the old hard-coded 1.0. However, now that we can capture much finer detail by using smaller filter width values, using a high distance value can suddenly amplify that fine detail and any subtle noise into something that looks overly harsh and just not right. This is precisely why carefully setting the distance parameter is now even more critical than before. So let's talk about the distance parameter's default value. It's set to 1.0. And honestly, for most common scenes modeled at a realistic real-world scale, like this chair scene that I'm using, a distance of 1.0 is approximately 4 orders of magnitude too strong. Modeling at a real-world scale is generally a recommended and efficient practice in 3D, so the default value of 1.0 is just egregiously too large for a lot of common uses. Consider this. A default bump distance of 1.0 is effectively trying to simulate a maximum apparent height of 1 meter. This 1 meter value is what influences how drastically the bump node adjusts the normals based on surrounding texture data. But that scale is completely unrealistic for the kind of subtle surface details we typically use bump maps for. Most common bump information, like the weave of fabric, wood grain textures, or surface scratches, is going to be sub-millimeter in height. Based on my experience, a much more appropriate starting point for distance, especially when working at real-world scale and leveraging the finer detail capture of a smaller filter width, is not 1.0, but something dramatically smaller like 0.0001. That's the equivalent of simulating a height of just 1/10 of a millimeter. And the problem is that we, the user, have to stumble around playing with these values, randomly adjusting strength and distance until we get something we think is right. The new filter width parameter adds to this confusion if you don't set distance correctly to start with. It's more critical than ever now. Now, a lot of users were already aware that the default distance value of 1.0 often felt too strong. But the old hard-coded filter width of 1.0 actually made it somewhat easier to use distance values that didn't really perfectly align with your scene's real-world scale. Meaning a filter width of 1.0 is generally going to be more forgiving of unrealistic bump values. So my strong recommendation is to always start with a distance of 0.0001 when working at real-world scale and make small, incremental adjustments from there. For example, try increasing the distance from 0.0015 to 0.002. You'll quickly find that even these small, minuscule changes can have a noticeable impact on the apparent height and depth of your bump. The necessary range of values for real-world scale is surprisingly small. While the new default filter width for fresh bump nodes in Blender 4.43 is 0.1, remember that this is just a starting point. You should absolutely feel free to experiment with higher filter widths, such as 0.25, 0.5, or even 0.75, or even going back to 1.0 if you think that's right. Capturing the absolute smallest details from your texture isn't always the best approach. Sometimes a slightly larger filter width can provide a smoother, more pleasing, or artistically desirable result. So here in this rendering, we've got this leather texture. This one actually uses a different bitmap that I created to drive the bump node, and it's got a lot of small detail in it. So this uses a filter width of 1.0, which is the backward compatibility value. If we take it down to 0.5, look what we get. We get just a little bit more of the shading information from the bump node affecting the roughness. Let's take this down to 0.25, and we further increase that effect. Now, if we go all the way down to 0.1, which is the new default, we end up getting this. And in my mind, that's just way too rough. So what I did was I backed off the filter width to 0.2, but I also changed the surface roughness in the principled BSDF and lowered it from 0.17 to 0.1. And I think that gives a really nice surface appearance. Now, one issue that you can run into that I've mentioned is that if you have noise reduction turned on, it can struggle to maintain that. And this image does not have noise reduction. If I turn on noise reduction, then we get that, and you can see it kind of smudged out the surface in a few areas. So I hope you can see that this new filter width function gives you much more nuanced control for surfaces that have bump mapping.